Section 2.1, measures of relative standing and density curves. Measures of relative standing are called z-scores. When we calculate a z-score and are standardizing the value, we are converting scores from original values to standard deviation units. If you can imagine, I have a long stick here. It's got three sides on it, so it's triangular. On one side, I have the units in inches. On another side, I have the unit in centimeters. And on the third side, I have the value in z-scores. And I was going to measure each one of your height. I stand the first person up, I measure them, and I say, oh, you are 68 inches tall. Now I spin it around, you're this many centimeters tall. I spin it around a third time, and now I tell you your height in z-scores is 1.1. Okay, all a z-score is a different unit that we measure in. Okay, if x is an observation from a distribution that has a known mean and standard deviation, the standardized value of x is given by, where we take that value minus the mean and divide by the standard deviation. So what we are measuring is the number of standard deviations you are above or below the mean. The standardized value is often called a z-score. If z is positive, that means that you are taller than the average person. If z is negative, then that means you are below the mean. It means that you are shorter than the average person. And the absolute value of z simply tells you how many standard deviations the score is from the mean. So it matters whether you have a positive z value or a negative z value. So make sure when you're talking about z-scores that you are doing so in reference always to the mean. So if you say that you are 2.1 standard deviations away from the mean, identifying whether that is above the mean or below the mean, because obviously there is a big difference between those two things. First example here. Three landmarks of baseball achievements are Ty Cobb's batting average of 420 in 1911, Ted Williams' 406 average in 1941, and George Brett's 390 average in 1980. These batting averages cannot be compared directly because the distribution of major league batting averages have changed over the years. The distributions are quite symmetric except for outliers such as Cobb's, Williams, and Brett. While the mean batting average has held roughly constant by rule changing and the balance between hitting and pitching, the standard deviation has dropped over time, which means what? If the standard deviation is dropping over time, it means that there is less variation over time. Here are the facts. In the 1910s, the mean batting average was 266. The standard deviation was 0.371. The 1940s, when Ted Williams hit 406, the mean batting average was 267, standard deviation 0.0326. And in the 1970s, when Brett hit 390, the mean batting average was 261, and the standard deviation was 0.0317. So what we want to do is compute the standardized batting averages for Cobb, Williams, and Brett to compare how each stood compared to their peers. So let's start with Ty Cobb. We want to find the z-score for Ty Cobb. We're going to take his average, which was 420. We're going to subtract the mean for that period of time, which was 266. And we're going to divide by the standard deviation of 0.0371. Plug that into your calculator, you get a z-score of 4.15. So there's Ty Cobb. Ted Williams hit 406. Mean batting average during that decade was 267. Standard deviation 0.0326. Plug that into your calculator. His z-score was 4.26. Last one, George Brett. George Brett hit 390. mean batting average in the decade was 261. The standard deviation was 0.0317. His z-score is 4.07. Again, the z-score is measuring how many standard deviations above or below the mean that a certain value is. The farther it is away from the mean, the more unusual the value is. So in this case, Ted Williams, 4.26 standard deviations above the mean, was farther away from the mean in his decade than were either Ty Cobb or George Brett. So if we wanted to answer the question, which one of these appeared to have the best batting average relative to the time period in which they play, we would say that Ted Williams had the highest average, relatively speaking, meaning comparing that batting average to his peers within that decade. So a z-score allows us to compare things like this that have different means and different standard deviations. It allows us to come up with a standardized value that allows us to compare amongst generations here or anything else that we may want to compare. Measures of relative standing, we can talk about it in terms of percentiles. The empirical rule, first of all, the empirical rule only applies for symmetrical distributions. If you have a skewed distribution, you cannot apply the empirical rule. The empirical rule tells us that if it's a symmetric distribution, that we should have 68% of the observations falling within plus or minus one standard deviation from the mean. 95% of our observations should fall within two standard deviations from the mean. And finally, 99.7% of the observations should fall within three standard deviations of the mean. So you can see it is very rarely in a symmetrical distribution to have anything farther than three standard deviations from the mean. Notice all of these were more than four standard deviations for the mean. So how did they compare to other hitters within each of their generations? Obviously, that season they were quite a bit better than everybody else. We can use the empirical rule then to make some general statements about things, which we will look at in some examples, graphically looking at the empirical rule. Remember, we're talking only about symmetrical distributions. So we have X bar here in the middle. Okay, we would have 50% of the data points above the mean, 50% below the mean because we're talking about a symmetrical distribution. And since we have 68% within plus or minus one standard deviation, that means we have 34% on each side within a standard deviation. So between X bar and X bar plus one standard deviation is 34% of the data. Likewise, if we have 95% within two standard deviations, that means between the first and the second standard deviation is 13.5%. Same thing over here. And finally, outside of that, within three standard deviations, we get another 2.4%. And out in the extremes, larger than three standard deviations, we have 0.1% and really 0.15. They've rounded this chart to the 10th position only. Okay, but you get the idea of how we can use the empirical rule with symmetric distributions. Well, what if the distribution isn't symmetric? Then we can use Chebyshevs inequality. Chebyshevs inequality is not quite as accurate as the empirical rule, but we can use it in estimating the number of observations within a specified number of standard deviations from the mean for any distribution. And that's the key to Chebyshevs inequality, which allows it to be used a little bit more than what the empirical rule is in any distribution. So regardless of whether it's skew left, skew right, or symmetric, we can find the percent of observations falling within k standard deviations of the mean using this formula. And because this is a formula that works with any shape of a distribution, you can imagine that it's not quite as accurate as what the empirical rule is, for instance. So let's say that the first thing we want to find is for k equals 1. So what Chebyshevs inequality is going to tell us, when k equals 1, it's going to tell us the percent of observations that fall within one standard deviation of the mean is at least this value. Well, if we plug 1 in there, what are we going to get? We're going to get 100 times 1 minus 1, which is 0. Doesn't tell us a whole lot. It says that within one standard deviation of the mean that there will be at least 0 observations. Not real helpful. How about within 2 standard deviations of the mean? Well, now we have 100 times 1 minus 1 over 2 squared, which is 1/4. We get 75% of the observations. So what does that tell you? That in any distribution, the percent of observations falling within 2 standard deviations of the mean is at least 75% of our observations. Let's go out one more. 3 standard deviations. Well, in 3 standard deviations, we're going to have 100 times 1 minus 1/9, which tells us that there are at least 89% of the observations within 3 standard deviations of the mean in any distribution. Problem 6. Refer to the previous exercise. The December 2000 unemployment rates for the 50 states had a symmetric single peak distribution with a mean of 3.47% and a standard deviation of about 1%. The unemployment rate for Illinois that month was 4.5%. There were 42 states with lower unemployment rates than Illinois. So talking about the year 2000. Write a sentence comparing the actual rates of unemployment in Illinois in December 2000 and May 2005. So December 2000, the unemployment rate in Illinois was 4.5%. In May of 2005, and that's using this chart here out of the book, in May of 2005, we can look at Illinois and see that the unemployment rate was 5.8%. We want to write a sentence comparing the actual rates of unemployment in Illinois comparing December of 2000 to May of 2005. Well, if we look at this and we want to know, well, what's the percent change from December of 2000 to May of 2005? And you need to be careful when you compute this. You can't just look at this and say that it went up by 1.3% because there's more to it than that. Percent change is always found by taking the old amount minus the new amount, dividing by the old amount, and multiplying it by 100 to change it into a percent. So in this case, the unemployment rate started at 4.5%, went up to 5.8%, multiply that by 100, and we see that that actually is an increase of 28.89%. So write a sentence comparing those actual rates of unemployment from December of 2000 to May of 2005, and we can see that Illinois unemployment went up by 28.89%. From December of 2000 to May of 2005. Part B, compare the z-scores for the Illinois unemployment rate in these same 2 months in a sentence or two. So let's first calculate both of these. Starting with December of 2000, calculating a z-score, take the Illinois value, which was 4.5, minus the average, which was 3.47, divided by the standard deviation, which was 1%, and we get a z-score of 1.03. In May of 2005, well, first of all, some information that was given in the previous problem that you need to know here is that for May of 2005, the mean value was 4.896. Standard deviation was 0.976. So for Illinois in May of 2005, if we want to find the z-score, I'm going to take the Illinois value, which is 5.8%, minus the mean value of 4.896, divided by 0.976, and we get a z-score of 0.93. Okay, so comparing these two z-scores, which one did Illinois have a smaller unemployment rate compared to the national average? Well, this would indicate to us that in May of 2005, the unemployment rate was less than December of 2000 compared with the national average. Letter C, compare the percentiles for the Illinois unemployment rate in these same 2 months. Well, if we look at the percentiles, let's again start with December of 2000. It tells us that there were 42 states. There were 42 states with lower unemployment rates than Illinois. So that means Illinois would have been the 43rd state out of 50, which puts them in the 86th percentile. In May of 2005, if we look at our chart here, there's 1, there are 8 states with more than, if you go through and look at all the ones that are bigger than 5.8, there are 8 states larger, which means Illinois would have been the 41st state out of 50, putting them in the 82nd percentile. So again, comparing the 2 percentiles, we would say that Illinois was in a better situation in May of 2005 than December 2007. Using percentiles, Illinois had a lower percentile in May 2005 compared to December of 2000. So you can see there's a lot more to look at rather than just simply looking at the raw percents that we had here, where you would look at this and say, well, geez, in December of 2000, there was over 1% less unemployed in Illinois than there was in May in 2005. If you go a little bit deeper into the numbers, you can see, relatively speaking, Illinois people were better off in May 2005 compared to the entire United States than they were in December of 2000. Get the next example. Larry came home very excited after a visit to his doctor. He announced proudly to his wife, "My doctor says my blood pressure is at the 90th percentile among men like me. This means I'm better off than about 90% of similar men." How should his wife, who is a statistician, respond? Well, when we're talking about percentiles, remember a percentile tells you how many are at or below your level. So him being in the 90th percentile for blood pressure means that 90% of men similar to Larry have the same or lower blood pressure than he does. So in this case, even though the 90th percentile sounds like a good thing because it's almost 100%, 90th percentile is bad in this situation because most men have his blood pressure or a lower blood pressure than what he has. Density curve. Okay, a density curve simply, and remember when we were drawing histograms back in chapter 1, we did this where we kind of drew the curve over it to help us identify the shape. Okay, when we're talking about density curves here, it's just putting a smooth curve over this histogram. A density curve is a curve that, and these are important characteristics, it's always on or above the horizontal axis, and here's the key, has an area of exactly 1 underneath it. A density curve describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. Okay, so the density curve, the key is it's always on or above the horizontal axis, and it has an area of 1, and that's going to lead us into a bunch of different things later on in the class. The median of a density curve is the equal areas point, the point that divides the area under the curve in half. The mean of a density curve is the balance point at which the curve would balance if it were made of solid material. The median and mean are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. That's the same stuff we talked about with identifying shape. Mean is always pulled in the direction of skewness. The mean of a density curve is mu. So now we're introducing some population variables. Density curve represents a population. Mean is mu. Remember, a sample mean is given by x bar. Standard deviation of a density curve is given by the Greek letter sigma. Remember, standard deviation for a sample is just given by the letter S. Statistic correlates to sample. Parameter correlates to population. So in this case, we are talking about population parameters, mu and sigma. The sample statistics would be x bar and S. So again, for a statistic or sample, the mean is x bar. Standard deviation is S. A parameter measures a population value. Mean is given by mu. Standard deviation is given by sigma. Problem 10. A uniform distribution displays the density curve of, figure 2.8 displays the density curve of a uniform distribution. The curve takes the constant value 1 over the interval from 0 to 1 and is 0 outside the range of values. This means that the data described by this distribution takes values that are uniformly spread between 0 and 1. So we can see on this density curve here, the x-axis goes from 0 to 1. The height of the curve is from 0 to 1. So the area underneath this curve would be 1 times 1, which is 1. And remember, the area under any density curve has to be equal to 1. Use areas under this density curve to answer the following questions. First one, what is the total area under the curve? Well, how do we find the area of a rectangle or square in this case? B times h, base times height, which is 1 times 1. The area is 1, which we know has to be true if this were a density curve. What percent of observations lie above 0.8? Well, if we go back to our graph here, there's 0.8. We want to know what percent of observations are then in this area right here. Well, what's the area of this rectangle? The base is 0.2. The height is 1. So if we want to find the area, take 0.2 times 1. The area is going to be 0.2, which means about 20% of the observations lie above 0.8. What percent of the observations lie below 0.6? Do the same thing on your curve. 0.6 is about in here. So we're looking for that area to the left. The base of that is 0.6. The height is still 1. So what percent of observations would lie above that? 0.6 times 1 means that about 60% of the observations are less than 0.6. What percent of the observations lie between 0.25 and 0.75? Well, between 0.25 and 0.75, it's 0.5, or 50% of the observations. The last one, what is the mean for this distribution? The mean is in the middle, which is going to be 0.5. All right, last thing here, finding means and medians. Figure 2.9 displays 3 density curves, each with 3 points indicated. At which of these points on the curve do the mean and the median fall? First of all, let's identify the shapes here. This first shape is going to be skew to the right. Second one is going to be symmetric. And the third one is skew left. Okay, we need to identify where the mean and the median are for each one of these. Okay, let's add one other thing in here. I think it will help you a little bit. Let's also talk about mode. That's the easiest one to identify of the 3. Where's the mode? In our first graph, mode, remember, is the most, highest point, A, and this one is at point C. Let's go to B first, the symmetric distribution. What do we know about the mean, the median, and the mode? If it's a symmetric distribution, they should all be the same. So the mean and the median are also at point A. Let's go back to letter A here now. Median, remember, is 50%. 50% to the left, 50% to the right. Median has to be at point B then. And the mean, remember, is greater than the median in a skew right distribution. Pulled in the direction of skewness, the mean has to be at point C. If we look at our last distribution, our skew left distribution, median 50% to the left, 50% to the right is going to be at point B. And our mean then is pulled in the direction of skewness, which has to then be where point A is. Last slide again is just a review. Make sure you read through that. If there are things you don't understand, bold words that you do not know the definition, make sure you are getting to know those. If there are conceptual things that you're not sure about, make sure you are getting extra help on those items.